in terms of science, technology, and medicine if we could reduce the time it takes to turn ideas into reality, and if more people had the opportunity to pursue their creative or to reach their creative potential. Goodman writes, our progress has been largely a matter of inventing new tools and improving the old ones. One type of tools are development platforms like those pictured here. Platforms play two critical roles in how they enable progress. First, by lowering barriers to entry. First, by lowering barriers to entry for novice users, and second, by enabling rapid prototyping for experts. Take, for example, Raspberry Pi and Arduino, and consider the impact these platforms had in the fields of physical computing and electronics, respectively. They not only made these fields accessible for novice users, but they also made it possible for experts like us to prototype projects incredibly rapidly. An electronics project that 2 decades ago may have required engineering expertise and a week of work in a lab with expensive equipment, today that same project can be done in a weekend by a high school student in their living room. Now, previously, I used to think that platforms alone were responsible for this kind of transformation. But after many years of using, studying, and developing platforms myself, I realized that what enabled this transformation is not the platform alone, but a whole ecosystem that emerged alongside the platform. Because even if you have the most amazing technology, it will not be adopted widely unless there is also an entire ecosystem around it to support it. And so over the past 2 years, I have been trying to capture the essentials of what it takes to design and deploy a platform for wide-reaching impact. And I identified 5 essential requirements. First is to have a complete technology package, usually consisting of both hardware and software. The platform must be general purpose, easily extendable, and bring value not only to new users, but also to experts. Second is content, to showcase what is possible with the platform and to inspire people to unleash their creativity. This should include projects made by different users, tutorials, and videos. Third is the community and interactions. The community enables the platform to have a wide-reaching impact, not only because they can contribute inspiring applications, but also because of the network effect. The larger the community around the platform, the more valuable it becomes to everyone using it, as in the case of many other platforms taking advantage of the network effect. Fourth is an online community platform, a website that can facilitate these interactions between people. Users need a place where they can ask questions, showcase their work, get help, and find collaborators. And finally, what's absolutely critical is a viable deployment model. The platform must be available and accessible to people. People need to have a way of obtaining it. And this must happen in a financially sustainable way for the project to survive long term. Consider, for instance, a popular platform like Arduino. It has all of these characteristics. It is a general purpose hardware and software that is valuable to both experts and newbies. You can easily find thousands of inspiring projects and tutorials online and millions of users from all diverse backgrounds and age groups. There is not just one, but many websites dedicated for the Arduino community. And finally, the deployment model has been highly successful in terms of global impact. I also identify several feedback loops within this framework. The platform enables new applications, which then inspire additional features, enabling even more diverse applications. Most applications are provided by the user community, and the more inspiring projects there are, the more attractive the platform becomes to new users, who then make even more projects with it. And there are many other such feedback loops, which I cover in my extended 1-hour talk, but I won't be discussing here. Soft robotics and dynamic materials are becoming increasingly more relevant to people from diverse fields and all kinds of backgrounds, using them across a wide range of applications, including interfaces, haptics, interactive art, and countless more. However, when working on soft robotics projects, people usually spend majority of their time developing electronics and software and hardware rather than the actual application itself, which they're ultimately trying to achieve. And this creates significant inefficiencies, stifles innovation, and even discourages the pursuit of many ideas. People then end up with projects like these where the control system is actually far bigger than the actual project. What is needed is a general purpose platform, just like Arduino or just like Raspberry Pi, for actuation, sensing, and control of dynamic materials that is suitable for both experts and novice users, enabling them to rapidly develop new applications. And in fact, not just a single platform, but multiple platforms suitable for various kinds of actuation, including pneumatic, hydraulic, electromagnetic, and others, which are common in the soft robotics field. However, the most common approach today, by far, in my view, is pneumatics. And that's why I began this journey by developing a general purpose pneumatics development platform called Flow.io. Inspired by how Arduino transformed electronics prototyping, I wanted to create a platform that would transform soft robotics prototyping in a similar way. But to achieve this kind of transformation and to have large scale impact, I had to focus not only on developing powerful and user-friendly hardware and software, but I also had to create a whole ecosystem around it. And in the rest of my talk, I will summarize some of the work I have done across each of these 5 areas, starting with the Flow.io hardware and software. Flow.io is the first fully integrated and truly general purpose miniature pneumatics development platform for actuation, sensing, and control of soft robots. Flow.io comes as a complete package of modular hardware and intuitive software that is highly user-friendly. It has 5 pneumatic ports where each port supports inflation, vacuum release, hold, pressure sense, and flow rate variability. It has multiple connectivity options as shown on the right. And you can also connect multiple Flow.io devices together via Bluetooth if you want to have more than 5 pneumatic ports. The platform is fully modular and comprised of magnetically connected modules that can be swapped within seconds to satisfy different requirements and user needs. A main module serves as a pneumatic multiplexer with various sensors, and 3 pump modules enable Flow.io to satisfy different needs for pressure, flow rate, and size just by choosing the appropriate module. Expansion modules and accessories provide additional sensing, control, and mounting capabilities. The main module contains 7 valves in a manifold configuration, 2 custom-made circuit boards, a microcontroller with Bluetooth, as well as a 600 milliamp hour LiPo battery that powers the device, and there is also an integrated battery charger. Additionally, there is a large number of sensors, about a dozen of them, including proximity and IMU, and all of this fits inside a very compact 3D printable snap fit enclosure. One of the pump modules is shown here. It has 2 pumps, a 500 milliamp hour LiPo battery, a PCB with power electronics, and it also has its own battery charger. Thus, you have a fully integrated solution requiring no external pressure or power sources. The entire device with the small module weighs only about 110 grams and can even fit inside a pocket. Here I show, Here I show a comparison of the inflation and vacuum capabilities between the small and the medium pump modules. And I also demonstrate how you can easily swap one set of pumps for another, even with the device on, without any interruption of the Bluetooth connection. Here is the pneumatic circuit for Flow.io. There are 7 valves connected to a manifold shown in green and 2 pumps. There is also a pressure sensor connected directly to the manifold line. And in this general configuration, 1 pump is used for inflation and the other for vacuum. However, the device also supports 4 additional configurations where the pumps can be placed in series or in parallel if you want to achieve higher pressures or higher flow rates. Switching between configurations takes only a few seconds and is done using an external tube that goes around the pump module. The table here shows the pressures and flow rates that can be achieved for each of the 3 pump modules across the 5 configurations. For instance, in the general configuration, with the medium module, you can have pressure ranges from -13 psi to 22 psi, but if you change modules and configurations, you can achieve pressures as high as 30 psi. A limitation of this pneumatic circuit is that it uses a single pressure sensor to monitor pressure across all 5 channels via time multiplexing. And while for most applications this is sufficient, there are some applications where a single pressure sensor is limiting. And that's why I developed a module which I call Sensors++, that provides 5 additional pressure sensors at the outputs of the 5 ports. And this is how the module looks, and it goes underneath the main one as shown on the image. There are many other modules for different sensing and actuation needs, including 2 new ones not even shown here, and I talk about those in my extended talk, but I won't go into details here. The pumps of Flow.io are open to the external world, as shown by the 2 arrows, but you can easily convert this to a fully closed system by connecting those to an air tank, or you can even connect them to a water tank, and now you have a hydraulic system, not just a pneumatic system. Finally, you can also replace the pump module with a compressed air tank to achieve much higher pressures. We were successfully using this configuration to achieve pressures and to use them, in fact, in a project that were 70 psi. So that was hardware. Now let's move on to software. Flow.io has a graphical user interface and multiple libraries and APIs, making it suitable for people from any technical background. The graphical user interface was built in JavaScript and implements the Web Bluetooth protocol, which allows your Google Chrome web browser to directly connect with Flow.io device. And this enables you to control Flow.io from any device and any operating system that supports Google Chrome. And the best part of it is that you don't have to download or install anything. You literally simply have to, if we play this, maybe it's the country. Oh, okay. I'm gonna skip this video then. Let's try this one. Okay. So it plays on mine, but not sure why it doesn't play on that. Yes, let me just. So task scheduling is also possible on the interface as shown in this example, and users can create a sequence of any number of tasks, and an interactive graphic on the left shows the state of each internal component of a connected Flow.io device in real time. Users can also write their own code for Flow.io with APIs and libraries have been developed for both Arduino and JavaScript. Shown here is the software stack for Flow.io, which one can choose to work at any layer of this stack. At the bottom is a pneumatics driver, which controls primitive tasks involving single pneumatic components. Then the second layer of the stack is a pneumatic API controlling entire activities and combinations of components, which is an abstraction of the driver layer. The third layer is what I call command API, and it makes every feature of Flow.io accessible via 3-byte commands. All of this functionality I then further abstract into a set of 7 Bluetooth services with 15 characteristics. A layer above that is a web API, which is a JavaScript layer that allows you to connect to Flow.io via Bluetooth directly from your web browser. And a unique feature of this layer is the ability to control up to 7 devices simultaneously and synchronously. And on top of that is a graphical user interface that implements just a few of the characteristics of the previous layer. And the final layer is peer-to-peer networking, which is to allow Flow.io devices to communicate with other Flow.io devices across the internet. This one is still in development. And this then opens a whole new world of application possibilities, such as remote collaboration and remote telepresence. Other notable features of the device are shown here, like auto-off timer, battery level indicators, and much more. And I also implemented a power saving algorithm as shown on the right side of the screen, where I'm exploiting the fact that for a solenoid valve, you need strong magnetic field only to open the valve, but then once the valve is open, you can actually reduce the current just to maintain it in the open state. And this allows me to reduce battery consumption by about 50%. And it also prevents the device from overheating. So the best part about the hardware and software for Flow.io is that they were designed in a very general purpose way. While this is a pneumatics development platform, most of the hardware and software is completely agnostic to the type of actuation. And that was specifically made with the intention for when developing these other platforms shown on the bottom here, they're going to reuse exactly the same hardware and software architecture, just small modifications made to those. So moving on to the second part, which would be much shorter, Flow.io has enabled people in about 10 countries to create a very broad range of applications. Here are some of the ones that have already been completed, and there are many, many more which are currently in progress and thus not shown. The projects to date fall into the following categories: haptic feedback, interaction design and art, assistive technology, locomotion, fun and play, and wellness. And in the next few slides, I'm going to show you quickly some of the projects that we have already published. Bubble is a wearable system that enables grasping augmentation without bending the fingers. Omnifiber. Omnifiber is a reconfigurable fiber technology for designing movement-based interactions using thin fluidic fiber actuators with strain control. And Three Voices is an opera performance done in Sweden that augments the listening experience with tangible interactions. It uses Omnifiber and 18 Flow.io devices that are synchronized to the rhythm of the music to deliver haptic feedback to listeners and enable a very immersive listening experience. NewBots is a modular construction kit for playful exploration of soft robots. It consists of 7 types of self-foldable segments with high tensile strength, and the kit enables various assemblies to be made with the modular pieces, allowing people to explore soft robotics in playful ways. We even had a Flow.io device go into a zero gravity flight, which is a peristaltic suit project. This was published, in fact, this week. And the goal of this project is to reduce some of the negative effects caused by prolonged exposure in microgravity environments. And these are just a few of many other projects enabled by Flow.io, which brings us to community and interactions. Here is a traffic map of the softrobotics.io website with over 8,500 unique visitors from every part of the world. Flow.io devices have now been used by dozens of people in about 10 countries. Many of those have been provided as a resource that can be shared across multiple people at those locations, as in the case of research labs. Here are some statistics about the community. There have been about 200 project proposals submitted to date, and of those, about 20% have been accepted to receive Flow.io devices. The project has also won many awards in research, engineering, and design. Last year, it won first place at the ACM Student Research Competition at CHI, as well as the Hackaday Grand Prize. And just this month, Flow.io was announced as the winner of the Create the Future Grand Prize award, which will be happening in a couple of weeks, the ceremony. So the community aspect of this project, of course, would not have been possible without the softrobotics.io website. And on this website, you will find detailed information about the project, including the motivation behind it, videos, documentation about Flow.io, and the graphical control dashboard. Under the community tab, you will find the history of projects created by the community, demonstrating different application scenarios and offering inspirations for new users. If you create an account, then you can also access an 18-chapter tutorial on how to replicate this device. This brings me to the final component of this framework, which is having a viable deployment model. Each Flow.io costs hundreds of dollars to make, and yet I wanted to make it widely accessible to people with creative applications ideas. And so for inspiration, I studied deployment models and initiatives and philosophies from various other projects. However, none of those were directly applicable to my objectives. But after taking some of the best parts from all of these concepts and leaving other parts out, I came up with a new deployment strategy or deployment model, which I named Creative Commons hardware, meaning hardware for creative applications belonging to the public commons. And under this model, the project is supported by donations, and any new units created are available to be borrowed freely for a limited time in exchange for any contribution made by the borrower. Contributions can be hardware and software development, writing tutorials and documentation, creating a YouTube video, helping with fundraising, graphic design, or anything else that helps the project grow and evolve. And once a user finishes using the device, then they're expected to return it so that someone else can use it or pass it on directly to another user. And in this way, the contributions made to the project benefit not only the entire community, but even the person making the contribution. And so I released Flowet to the world under exactly this distribution model. The device itself is provided freely to be borrowed to approved users who can do great things with it based on an application proposal that they must submit between 200 and 500 words. And the number of devices in circulation is determined by donations. The future goals for this work are to develop all of the platforms in this series and then go through all of the stages of this framework. And a vision for the softrobotics.io website is to become a go-to place for anything having to do with soft robotics, just like Adafruit is for electronics, or just like Stack Overflow is for programming. With this, I would like to acknowledge all of the people whom I had the pleasure to work with during the past few years who made contributions to this project. And I want to thank you all for listening and for inviting me to this talk.